Hello and welcome to the ON Semi wide-bandgap booth. I'm glad to have you guys around here again. ON Semi has been pushing for wide-bandgap to come into the market. And you know our famous wide-bandgap simulation tools. We're really looking to enhance customer experience, not only by providing a device, but to provide an entire ecosystem around things, right? There are now quite a couple of players out there that are providing devices to the market. And these devices are all fast, they're rugged. We know about their benefits of wide-bandgap. Silicon carbide is all around the trade show. Now the differentiation is missing, right? How can you provide a customer with tools to make their new product grow, right? We are all living in a time of exploring new opportunities, new topologies, right? So the first thing is provide a customer with tools they can simulate with. And that takes us to our physical simulation tools that we're providing. We're calling it, the ecosystem around wide-bandgap, fast switches, disruptive simulation environments. I'm just going to give you a short run through. I'm not going to run any live simulations. You can come to the booth and look at it. You can go to our webpage. There is a webinar on it. But the wide-bandgap benefits are clear, but the ecosystem is what we're offering, right? We're offering high-end drivers, right? These are, you don't only need a switch, you need something to drive it with. We have an evaluation board here that you can order online. It's with our NCP 51705, one of the forefront high-performance silicon carbide drivers. And we always say, you can run it with our device, but it's compatible with everything else too. However, it's tuned to our SiC MOSFET. We have the SiC diodes providing you the basics, but we have worked on diodes that are extremely rugged, and I want to then later on show you one of our most advanced tools. The silicon carbide MOSFET is coming out in the spring, in the fall, sorry, thinking about spring, in the fall time frame. And we have been working to give you a rugged product. We see applications are going to new switching speeds, to new temperatures, right? People are trying to reduce their cooling footprint, they're trying to increase their speed, and the question is, do I want to be fast to the market, or do I want to be out there with a reliable product? And we choose to be reliable. And then our physical models that enable customers to quickly prototype within a virtual environment, and not one that gives you just your SPICE model. This is something totally different. And I'm not going to run you through all the points. Where I want to come to is, I want to come to the fact how such a physical model is built up, right? Typical models in SPICE, they use the built-in, the built-in MOS model or something. People do curve tracer extraction, they populate parameters, there you go. These models are by far not what you want to do for system simulation. What we have done is, we have taken the real process flow of a device, the real geometry and the layout of our technology, and found a way to build physical models that take an abstraction of that device and put it into a simulation tool that you can use in SPICE. So what does that mean? For those of you who are familiar with device physics, a simple MOSFET, planar MOSFET with a vertical structure, so planar gate vertical structure like our silicon carbide MOSFET is, has different constituents that you can break down, like a JFET, like your epi layer, your drift region, your gate oxide. And you can just mask these as sub-circuits in SPICE. Now the real trick is to have sub-circuits for every one of these parts and make that physical. What does that mean? You implement equations that describe your sub-circuit as physical as possible and relate them to the real process parameter of the device. Now this becomes a physical model. It's not a curve tracer model anymore. It contains the real process. And you have things like doping in there. You have a real doping profile in SPICE. I mean, this is something you really got to wrap your head around. Now, you got the full geometric layout. In a SPICE model, we have defined things like gate path location. This affects your parasitics. This affects everything. This is what you want to have when you're doing system level simulation. And if you wonder how well it matches up against real measurements, this is what you get, right? You have some people, I have actually a bet running with our customers. I told them you should come in, measure one of our devices and run the simulation because he thought that can't be real. It is, right? We are hitting accuracies that are well beyond what you have in your traditional SPICE models. It's so accurate you can use the tool to predict devices' performance over temperature, something where you would only rely on a data sheet or some measurements from the customer or from your supplier. Now you can run this in simulation, RDS on over temperature, threshold voltage, body diode behavior of a MOSFET. It gives you a full flexibility to understand your device in simulation. Complex things like capacitances. These you cannot model easily unless you go into complex equations. But with these models, you have such a depth of physicality that you get things like the complex CRSS behavior of our MOSFET, which, by the way, the sharp drop that you see is very unique to our device, giving it its speed advantage. Or go into dynamic simulation, right? You can really go into dynamic simulation and study circuit-device interactions, and that's something we see as a necessity for wide bandgap development. Be it GaN, be it silicon carbide, you are approaching EMI behavior, you're approaching resonant and switching behaviors that will have tons of oscillations if not taken care of. And with this tool, you can study these things. And these models are also compatible with very complex simulators like ADS from Keysight, which can do a co-simulation between real circuit parasitics and your device. But that's not all. I want to take you to the next station. As I told you, ON Semi is really looking into making robust devices. And making robust devices means having an infrastructure that enables us to study our device under extreme conditions. We don't go off and buy off-the-stock tools. We develop them, and we make them in such a way that they can stress the device beyond what we imagine any customer is going to be running it at. And that will give the customer the trust, the data, right? And behind me is one of our young and skilled application engineers who has been the mastermind behind one of our really advanced tools in the wide bandgap team. And I'm proud to give over to him and let him explain about his little toy here.
So thank you, Meredith.
You're welcome.
So we are developing advanced testing in-house, as the industry standard tests are just not capable of covering all the challenges that wide bandgap applications will have for us in the future. So what we are looking at here is our in-house developed surge current tester. So usually a surge current was developed from the inrush current into a discharged capacitor on a rectifier from mains. That's why usually in the data sheets you will find half sine wave pulses, and you're giving a reliable data about the capabilities of covering a short current in this very high ranges of 8 times, 10 times of the rated current. So this is not the actual main focus for wide bandgap diodes anymore. It's not the bridge rectifier on the input of a power supply. It's more in switching power supplies where frequencies are much higher, where waveforms are completely different. That's why we developed a surge current tester that can take arbitrary waveforms, translate it into a current that is pushing through the device under test inside this device tester, and we can display the data with a built-in current and voltage probe and see the results in real time. So for a short demonstration, I will just shoot at a device under test, which is a 650 volt 8 amp silicon carbide Schottky barrier diode, which is rated for 8 amps. I'm going to do a 60 hertz half sine wave pulse with 70 amps of amplitude to see the behavior. So now we have stressed this device with a single pulse. As you can see on this screen, we will have the readout of the current in red. The scale is on the right, so we have a peak of 70 amps here, and we can see the forward voltage development in green. So the same graph we can see as an XY plot in here, where you can see the voltage and the current. So this gives us a very deep insight into what's happening inside our device. Usual surge current testers can only do a half sine wave pulse and give you the energy. Of course, we can give you the energy of this pulse as well. We can calculate it by the actual time-accurate measurements of current and voltage. So without going too much into the device physics, I would like to show the capabilities we have. We can go for arbitrary waveforms. So instead of giving you a half sine wave pulse, we can, for example, just arbitrarily use an M-shaped pulse to see the result of this very setup, of this very pulse there. So, as you now can see on the screen, we just have made the same pulse. We just entered in the software into our diode. We can see the voltage and current measurements accurately. What you can see is a different behavior for the two peaks we have in this. This is due to the self-heating in this device, which will eventually also degrade the device and lead to failure if the voltage, if the current is going too high. That's why we have this tester to actually guarantee values of currents and peak currents that will help us determine the SOA of the device. What we can also offer to our customers is the possibility to enter custom waveforms here. If a customer has a problem with a 30 amp peak which has a certain shape and asks if the diode is actually able to withstand this peak repetitively or over temperature, we can recreate this pulse in the setup, do repetitive tests even over temperature to actually give reliable data about the device ruggedness. So that concludes this presentation from my side. Back to Mervin.
I want to just add one or two remarks to this tester, right? Martin gave us an overview of the key features, right? Why these things become important is we have very different profiles from each customer, and the applications are becoming different. Actually, we have something here that can go from the nanosecond pulses all the way to second pulses. We really cover a broad range of knowledge, and this makes us one of the key differentiators, again, is quality. ON Semi is trying to bring wide bandgap with a reliability factor in it, where the customers do not need to worry about implementing these new technologies, right? So thank you. Thanks for your time.